Chapter 9 of the Seaborg text introduces the instrumentation that's used in control loops. Because we're studying this chapter a little bit out of sequence, there will probably be some content in Chapter 9 that refers to things that we haven't studied yet. For example, equations 9, 4, 9, 5, 9, 30, and 9, 31 represent transfer functions, which we'll introduce in the coming weeks. I don't want you to be too concerned about a few unfamiliar topics that appear in Chapter 9. We're going to focus on modeling the behavior of the instrumentation and components in control loops. And it's appropriate to introduce this material along with the material in Chapters 1 and 2, because Chapters 1 and 2 are also about modeling the dynamic behavior of processes. The diagram shown on this slide is an instrument diagram for a simple feedback control loop that regulates the temperature in a stirred vessel. The components of this control loop include a sensor, which is the thermocouple that detects, in this case, changes in temperature. In general, any sensor detects a measurable physical process variable, producing some response. Usually that response is an electronic signal, maybe a voltage in millivolts. The next component in the control loop is a device called a transmitter. The transmitter usually converts a signal from one type to another. For example, a signal might be converted from a scale of 1 to 5 direct current volts to an instrument signal that's 4 to 20 milliamps. The next component of the control loop is the controller. The controller takes the signal from the transmitter as an input, and it outputs a signal that can be used by an actuator. The controller output is computed based on the control law, or the design equation for the controller. The actuator is the final control element in the control loop. This is often a valve, or in this case, maybe a variable power supply that regulates how much electrical power is sent to the heater. Altogether, the elements of this diagram, including the process, make up what we call the control loop. The sensor and actuator are the parts of the loop that interact with the process, and therefore the sensor and the actuator are collectively referred to as the interface. Sometimes a sensor and transmitter are combined into a single component that we call a sensor transmitter. Some control loops have additional elements that are called transducers. Transducers are used to convert signals from one type to another, usually a current to a pressure, that is an IP transducer, or a voltage to a pressure, which is called an EP transducer. Here we use E for voltage because V is typically used for volume. Many final control elements actually operate based on a pneumatic signal or a pressure rather than on an electronic signal such as a voltage or a current. Sensors or sensor transmitters supply instrument signals that are usually on one of three ranges, either 4 to 20 milliamps for current signals, 1 to 5 volts for voltage signals, or 3 to 15 psig for pneumatic signals. Instrument signals might be represented by a variable with a tilde or by a subscript m. Our textbook uses both. The conversion factor between the actual temperature and the signal representing the measured temperature is called the steady state gain, K sub m, of the sensor. In this case, we're measuring a real temperature, T, and the thermocouple is capable of accommodating temperatures between some minimum and maximum, given by TH and T0. The instrument signal can take on any value between the minimum and maximum. If it's a current signal, it could be between 4 and 20 milliamps. So TM0 is 4 milliamps, and TMH would be 20 milliamps. This instrument gain then is the ratio of the output span to the input span, where the output is the instrument signal Tm and the input is the actual temperature that we would measure on a temperature scale, like degrees Celsius. Graphically, the steady state gain of the sensor transmitter is given by the slope of the line shown here, which relates the actual process variable T to the instrument signal T sub m. In this example, the input span is 100 degrees Celsius, and the lowest possible measurement is 50 degrees Celsius. The lowest possible measurement is called the zero, although it may not be numerically equal to 0. So the 0 is the lowest possible reading on either the scale of the process variable or the corresponding scale of the instrument signal. The span is the difference between the highest possible reading and the 0. While the span is a single number, the range is two numbers, representing the lower and upper bounds of the reading. The term resolution refers to the smallest interval between two measured values. The precision of a sensor transmitter is the standard deviation of repeated measures of the same value. Many measurements have a bias. A bias is a constant offset in measured values from true values. Most real sensor transmitters are incapable of instantaneously tracking the behavior of process variables. That is, the sensor transmitters themselves have their own dynamic behavior. A reasonable model for many sensor transmitters is a first-order ODE. In this example of the thermocouple, the rate of change of the measured value might be proportional to the difference between the actual process variable and the current measured value. Or there could be a first-order ODE with what we call a time delay. That is, the rate of change of the measured value is proportional to the difference between the measured value and what the process variable was some theta d time units ago. Here, tau m is a measurement time constant and theta d is the time delay. To understand why sensors and transmitters have dynamics, consider again the thermocouple. In this case, the thermocouple leads create a voltage that varies depending upon the temperature of a junction between two dissimilar metals. That junction is usually protected by a thermal well. The thermal well might just be a stainless steel coating around the thermocouple leads, or it could be lined with glass to protect it from corrosion, and then inserted into a process vessel where it's actually the thermal well that's in contact with the process fluid at temperature T. That thermal well itself has its own heat capacity and mass. So if the temperature of the process fluid were to instantaneously change, suppose the vessel were empty and at some ambient temperature T, and then a valve were opened and fluid flows into the vessel, submerging the thermal well into a fluid at a new temperature. Then we might model the temperature of the fluid as a step change from T at 0 minus to T at 0 plus, with a magnitude delta T. The response of this first-order linear ODE to a step change in the temperature T at time 0 is an exponential. That is, the measured temperature T sub m asymptotically approaches a final steady-state value with a time constant tau sub m given by mc over UA, where m and c are the mass and heat capacity of the thermal well, and UA represents the overall heat transfer coefficient and area of the thermal well. This means that the sensor transmitter cannot track instantaneous changes in the temperature of the process fluid. If the time constant for the measurement is small, that is, mc over UA is small, compared to other time constants in the process, that is, the time constants associated with expected changes in the temperature of the process fluid, or the residence time of the vessel, for example, then Tm will be a good approximation for T. However, if the process fluid can change much faster than tau m, then this sensor transmitter will not track those changes. If the sensor transmitter dynamic equation also includes a time delay, theta d, then the resulting measured temperature has similar behavior, only it will be delayed in time by an amount theta d. That is, theta d delays the sensor response. While we develop this idea for temperature sensors, other types of sensors can be modeled using similar equations. For example, level sensors or composition sensors can also be modeled by first-order ODEs. Sometimes composition sensors only contain a time delay. This is common when the composition measurement requires taking a sample, transporting that sample to a lab, and then analyzing that sample on an instrument. The resulting measured composition would give an indication of what the composition was when the sample was taken theta m time units ago, and not what the composition is right now. Many pressure sensors and flow sensors give very fast measurements. These can often be considered to be instantaneous measures of their respective process variables. Some level sensors are also based on a pressure sensor, in which case they can many times be essentially instantaneous. Composition sensors can be some of the slowest. Some composition sensors, such as pH meters or dissolved oxygen sensors, can be relatively fast, but other composition sensors, for example those that are based on a chromatographic technique, can have very long time delays associated with them. In the next video, we'll talk about designing control valves.